Watching a sunrise can be quite inspiring, and I've been inspired. We are going to calculate the distance to the sun using parallax, and we'll be overturning a 2,000-year-old assumption. You're in for a real treat, my friends. The heavens will be decoded, because those that seek shall find.
As you can see, the illumination is up, but the sun is down. You can tell the illumination is at 90 degrees, just about 90 degrees, but it doesn't connect with the sun, you know? So there's incredible light bending. The sun is not where it's supposed to be due to refraction, okay? It's much higher, but it has been brought down.
This is the beginning of a new era. Truth will rise again.
And it's going up like that. So that's where the sun is supposed to be, up there, not down there. Sun's supposed to be up there. So refraction brings the sun down. It makes it look like it's going down and up. Incredible stuff, folks, I'm telling you. This is crazy stuff, man. Crazy. There's a lensing effect.
By using a solar filter, I've been studying the angles between the sun and the moon for over a year now, and the results are just shocking. But before we get into that, let's dive into the parallax study, because this is very revealing. According to Wikipedia, parallax is a displacement or difference in the apparent position of an object when viewed along two different lines of sight. Very simple. As you can see in the animation, as you move left and right, objects in the scene change position relative to each other. Great article. You should browse it and read more about parallax used in astronomy, looking for stellar parallax, the challenges, the history, how they've tried to determine the distances in the solar system. Very, very interesting. But all throughout this article, you will see that they mention the stars. Reading the highlighted text, the moon, and to a smaller extent the terrestrial planets or asteroids seen from different viewing positions on the Earth at one given moment can appear differently placed against the background of fixed stars. So there you have it, measured against the background stars. But what if I don't want to measure against the background stars? I don't know how far the stars are. Why speculate about things that we can't really touch when we have references of distance on the Earth? Yeah, so we'll be using distant mountains, and we'll simply be measuring the distance to the sun and the moon. Just incredible, folks. Stay tuned for some amazing discoveries.
Morning, got up really early. I'm doing stereo images. I got my camera. I got my other one on the tripod. And I'm using a remote so I can trigger it. We'll see how it works. Sun's getting too bright, so I'm getting nervous. I don't want to burn my cameras.
The approach I took was very simple. Two cameras triggered at the same time. Obviously, I cannot be in two places at the same time. And so I had one hooked up to a wireless trigger so I could trigger it. And that way I could take two instantaneous photos of the sunrise and do calculations. Now, it didn't quite work as planned. The batteries in the transmitter or maybe the receiver were depleted and it appeared to be intermittent. It wasn't working at the distance that I wanted, so quite frustrating. Also, I realized that I needed better lenses to zoom in. So it was a learning experience. There's a lot to think when setting up such an experiment. For example, should I use a wide field of view? How wide? How narrow? Obviously, with the zoom lens, I can zoom in, but I'll have a narrower field of view. And that forces me to measure the sun at lower elevations, which is good because I am comparing it to features on the ground. Okay? And so if we use a wider field of view and we try to measure the sun higher up, then I'm going to need a solar filter so I don't burn my camera. But then if I put a solar filter on there, I cannot see features on the ground. So, the trace space is kind of interesting. So anyway, instead of doing too much thinking, I just said, hey, I'm going to do the Elon Musk thing. Just go out there and try it and see what happens. And some breaks, go back to the drawing board. So this was a first attempt, and I learned a lot, and I realized that I need a better technique, and I thought of an ingenious way of using only one camera. After the frustration of dealing with the transmitter and two cameras that weren't even identical, I was planning on scaling the images, etc. I realized it's too much work, too confusing, and I came up with a one camera solution. Just awesome. The technique is very simple. It involves taking 3 photos. So I start on the right at position 1, take a photo of the sunrise, making sure I could see the mountains in the distance clearly. Then I go to position 2, take a photo from there. Then I go back to position 1 and I take my third photo. And of course the sun is moving while it's rising. But because I have 2 photos at the right location, 1 and 3, I can interpolate the position of the sun because it's moving fairly constantly as it's rising. And thus I can bypass all the electronics and transmitters, and you don't really need 2 cameras with this technique. Very powerful and simple. Now here's the map for this experiment. The target is at 21.75 miles and it's a rock outcropping, and I use that in the images to align the images to that point. So that's what I call a pivot point, and it plays a crucial part in determining the angles and then the distances to the sun, as you'll see shortly. So I took 3 photos of the sunrise and aligned them to the front hills. And now when I toggle, notice those front hills to the left are stationary and everything else moves, including the sun. Now let's put a circle over the sun so we can do more exact calculations. So I've already done that. I'm just enabling the different objects. And so let's zoom in so you can see what's happening here. So there is the sun, and this is the first right image. Okay, and I have it centered pretty well, as you can see. Now we'll toggle visibility on the second image, and we'll get rid of the first disk and enable the second one. Look at that, almost perfect. Now we'll do the third one and toggle its circle, perfectly overlaid. Now let's zoom in and enable the 1 and 3 solar disks so we can find out where the second one should have been, since I changed location. So there's 1 and 3 enabled, and we'll look at the solar path. Okay, so I put a tangent between them, and let's zoom in a bit more. And now we can find out where the second position of the sun should have been had we stayed on the right side, but we went to the left side to take that image. Okay, so there it is. And now we're going to try to move it to the right. So let me enable it. Okay, so this is the sun position on the left, and now I'm sliding a copy to the right to figure out where the sun should have been had I taken the photo at the same time from the right side. Okay, so this technique allows us to do this calculation with only one camera. That's the beauty of it. Now here's the equations that help us determine the distance to the sun. If you're familiar with trigonometry and geometry, you should find this easy. Basically, we've aligned the photos to the pivot, okay, at a known location. Okay, and then we see how much the sun is shifting, distance c. And based on that, we can determine a number of angles and solve some equations. And we derive our equation. D equals R, the distance to the pivot, times angle A over B in radians. We're using a small angle approximation there. If now we have to use sine of A over sine of B. Fairly simple and straightforward. Very elegant. Shockingly, the distance to the sun came out to 5,778 miles. Just incredible. I couldn't believe it. But once I started calculating the air bounds, my excitement vanished. If I'm off by just 1 pixel, it brings the distance down to 973 miles. 2 pixels, 523. I said, wow, this is crazy. Looking at the difference that 1 pixel makes in terms of degrees, it is 0.00086 degrees. And the difference between theta and alpha is 0.00018 degrees. It's a quarter of a pixel. This difference between theta and alpha is actually the difference from the calculated position to infinity. Wow, I said, this is a sub-pixel problem. I need a resolution that's better than 1/4 of a pixel. I need a better sensor. I need a longer focal length. That's when I realized that this is no easy matter. This is not a walk in the park. You really have to think about this. And of course, there's turbulence in the atmosphere, and I got really discouraged. I said, yeah, I'm gonna have to bring a high-powered telescope, but then I need to put a solar filter, but then I cannot see the ground features only right when the sun comes up, and certainly I cannot run and move this heavy thing to another location. So I said I need 2 telescopes, and that's when I got discouraged, and I said, wow, yeah, this is a hard problem. It's not that simple, but something told me, hey, you're on the right path. Keep going. You know what you need to do. So I thought, okay, the simplest thing I can do is increase the baseline. For the second experiment, things turned out much better. And the reason is I increased the baseline to 127.2 meters, and that made all the difference.
That's my weapon, man. My weapon against reality. Love this camera.
So I walked from this utility pole all the way down there to the edge of the guardrail. And I used a laser rangefinder to find the distance as well. And then I confirmed on the map 127.2 miles. So that was my baseline. Now here's the image analysis. I'm flipping between 1 and 3 and there's no ground movement, okay? Now when I flip between 1 and 2, notice the ground, how it distorts. You see that? Yeah, very interesting. So I aligned to the second peak on the right, the pointed one. And now let's enable the solar disk. Wow, look at that. The first thing I noticed was the sun looked very elliptical, and it's more elliptical when it's closer to the horizon. So this time around I took photos of the sun when it was much lower on the horizon. Now zooming in, notice that we're dealing with bigger distances now, which is good. We're improving the data and minimizing the error. To further minimize errors, as before, we used the same size circles. I created the first one, curve fit, and then I just duplicated that 4 times in Adobe Photoshop, and then translated those circles to the proper locations. So this technique minimizes the errors, reduces the errors. So the results I got were just incredible, just blew me away, unbelievable. But before we look at that, let's look at the target, just to make sure we picked the right target, because the distance to the target is somewhat critical. Yeah, see, this was the pivot point out here. This hill, rock outcropping, whatever you want to call it, but it's got like a sharp peak on top. And I'm fairly certain that's what what I picked. And of course, if one messes up on the pivot point, then the analysis is wrong. But yeah, I'm fairly certain that's what I saw. I studied this quite a bit. It's the pivot. For the distance calculation, we'll first need to extract the shift in pixels. Zooming in, I came up with about 193, give or take 1 pixel. Plugging in the results, I was stunned. 258 miles. I calculated the air bounds, assuming plus or minus 2 pixels, and the results seem reasonable. It went from 291 miles to 231, so I thought, wow, okay, this is a lot more accurate. But I also double-checked the calculations. I couldn't believe my eyes. I said, what is going on here? Did I make a mistake? Is there lensing that's dragging the image? Not moving. Because the sun is compressed, as you can see, this means that the lensing effect through the atmosphere and curved space-time is of a divergent nature, not convergent, not concave. It's not a magnifying lens. And so I thought about the shift, right? As you saw earlier, I was moving the lens back and forth, and it affects, this lensing effect screws with the technique for parallax, and we cannot get accurate results, or so I thought. Little did I know that there was an error in my calculations, but everything leads towards enlightenment eventually. Because I got smaller values, I thought, now I can calculate the distance to the sun as it's rising and approaching us. So I decided to do a lot of photos as it comes up, walk back and forth, and get a series of photos to measure and see how the sun is approaching. And on this third occasion, I finally achieved my goal. Walking back and forth, I took 10 photos of the rising sun. Then I interpolated the missing information from left to right or right to left. And I put all this data into a spreadsheet and began to analyze it. Now, towards the top, the sun gets very bright and I couldn't quite curve it exactly. So I had to change the exposure around the solar disk. Trying to improve the curve fit, I decided to put a line from the first to the last to be more accurate. And that's when I discovered something very interesting. The sun actually curves up slightly relative to a straight line, not down. Very strange. As a result, I had to interpolate between each set of solar disks. A lot more work, but I wanted to be precise because every pixel counts. In addition, a fortunate thing happened. Since the sun keeps rising farther and farther to the left, since it's after the spring equinox, a great target came into view right there, this water tank. So very conclusive. I felt very confident about all these results. And that's when I realized my mistake. I did not take into account the skew relative to east-west. This effectively shortens the baseline. It's the green arrow relative to the yellow. Bad mistake. I can't believe I didn't think about it. I was just wrapped up in the excitement. But I had the data and I kept cranking and the results were just incredible. I've thought of everything, including the horizontal difference relative to the pivot. This was foolproof and it paid off. The distance to the sun came out to about 4,000 miles, folks. Curiously, same as the radius of the Earth. What is going on? As I pondered the mystery, I double-checked my calculations, and that's when I realized how everything had conspired together for good. Unbeknownst to me, I realized that now, by just varying 1 pixel, I am barely changing the average. I was averaging all the pixels, so in effect now, I am changing everything by 0.1 of a pixel. Just incredible. So I was able to achieve that sub-pixel resolution through averaging. And in retrospect, this is a no-brainer. It's done in astrophotography with multiple photos and everything, you know. So it was good. My intention was to get the proximity of the sun, but in actuality, it worked out good. Now, the other thing that's strange over here is that yes, some values are very sensitive. We have to pay attention to, accuracy on the baseline and everything. But notice the yellow and the green highlighted pixel counts. That seems to be oscillating. From the top, notice we get 207 pixels, then 212, then 205, then 212. Then 210, then 213, then 208, then 212. So I said, it's kind of interesting. The green ones seem to be very close to 212. They average to 212. And the other ones, a little bit more chaotic, but they're much lower. And that's when I realized what was really happening. Because the sun is actually curving up slightly, as we saw before, we overestimate on one side and underestimate on the other. When I realized that, I went, wow, yeah. I mean, look at the blue ones, the first and the third, right? 205, 207, 205. They go up against the red line, which is a segment between the adjacent. But as we saw, they kind of slowly curve, right? It's a slow curve upwards and just a few pixels off, but it's critical. Here the blue lines are exaggerated. I just put those in there so we can see it at this scale. But just a slight curvature of the path of the sun as it obviously moves towards the right and up. It's not quite a straight line, and it's not curving down either. It's actually curving up slightly. So that's what's doing. That's what's changing the numbers and why they appear to oscillate. Because as you can look at the interpolated images, the blue ones of the sun, we go right, left, right. So it's oscillating. So I thought, wow, how fortunate that I started doing this experiment, because now I can get an average. Before, I was in air. I was biased to one side too much. When I did just three, photos, I went, wow. So this worked out for good. So what was the bad assumption? Well, 2,000 plus years ago, there was a fellow by the name of Eratosthenes of Cyrene. Wikipedia has something very interesting on him. Besides how you pronounce and spell his name there, it says he was a Greek polymath, a mathematician, geographer, poet, astronomer, and music theorist. He was a man of learning, becoming the chief librarian at the Library of Alexandria. Wow. Yeah, that's a prestigious thing. The Greeks was very smart, His work is comparable to what is now known as the study of geography, and he introduced some of the terminology still used today. He is best known for being the first person to calculate the circumference of the Earth, which he did by using the extensive survey results he could access in his role at the library. His calculation was remarkably accurate. He was also the first to calculate the tilt of the Earth's axis, which also proved to be to have remarkable accuracy. He created the first global projection of the world, incorporating parallels and meridians based on the available geographic knowledge of his era. Eratosthenes was the founder of scientific chronology, yada, 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 yada. Look at the bottom paragraph. I thought that was funny. He was a figure of influence in many fields. According to an entry in Suda, a 10th century encyclopedia, his critics scorned him, calling him Beta, the second letter of the Greek alphabet, because he always came in second in all his endeavors. You Beta. Oh my God, that's funny. Nonetheless, his devotees nicknamed him Pentathlon, after the Olympians, who were well-rounded competitors, for he had proven himself to be knowledgeable in every area of learning. Yeah, quite an interesting fellow. Apparently he was from Cyrene, so I looked that up. I was kind of curious. Yeah, here's an old map, and I pulled a picture of the ruins from Cyrene on the Libyan coast. Yeah, it's very interesting. Apparently, that area bred a lot of smart people. Maybe they had a lot of resources, food, great weather. I don't know, maybe they ate too many dates from the date palms. And that increased their brain capacity. Who knows? But they're thinkers, Us, human beings, we like to explore and understand. We're endowed with this curiosity about our world. But let's look at his experiment. So apparently not much survived. Somebody else writes about him. So this Cleomedes, So let's read from the top. The measurement of the Earth's circumference is the most famous among the results obtained by Eratosthenes, who estimated that the meridian has a length of 250,000 stadia, with an error on the real value between 2.5% and plus 0.8%. Eratosthenes described his technique in a book entitled On the Measure of the Earth, which has not been preserved. Yeah, that's probably because the library at Alexandria burned down. Yeah, terrible. Anyway, the method being described there is quite simple. You can see in the graphic. They assume that, or he assumed that the solar rays come in parallel because the sun is really distant, and so any difference in shadows at a different location relative to where the rays fall normal to the surface or straight down is all due to curvature. And there was a place in Alexandria where, they knew that during the solstice, the sun is exactly overhead at noon, just perfectly, boom, right above. And then at a different location, you can measure the angle that the shadow is cast on the ground. So here's a better graphic I drew. So up top, Eratosthenes assumed distant sun and thus parallel light rays for all practical purposes, which implies all shadow differences are due to Earth's curvature. That is bad. That's a crazy extreme on one end. In many ways, the flat Earth and the curved Earth of the known radius are extremes. In one model, you're assigning everything to a curvature, assuming light travels in a straight line, being ignorant of curved space-time as Einstein has shown, and the effects of the atmosphere. Bad assumptions, but what do you expect? They did the best with the knowledge they had. Now we know better. We have satellites in orbit and exciting things. Make sure you guys keep watching, because I work in the space industry. I'm an engineer. I've been to all sorts of places, worked on UFOs. I have a lot of information, and you may be wondering where I'm getting all this inspiration. Just keep watching. I've been a flat earther for a long time, working in a vacuum, trying to convert some of my friends. Yes, the world is incredible, friends. So, as you can see, the other extreme is the flat earth. Okay? But is it really an extreme? Yeah, makes you wonder. Using parallax, we can calculate the true distance to the sun. And there's obvious lensing that's going on. Incredible stuff, folks. We can defeat the lensing effect with parallax, folks. You see, the lensing effect occurs in the vertical dimension, as we can see from the sun. Just seeing that ellipticity ought to make us wonder, like, hey, what's going on? But moving left to right relative to, the direction to the sun, or perpendicular to the direction to the sun, now we can defeat the lensing effect because it's acting the same at either locations. Yeah, just incredible, folks. We can get a direction to the sun, a distance to the sun, based on parallax, comparisons to features on the ground. Why look at the stars? Why assume something that you cannot touch? Okay? That's the error that people have made and continue to make in astronomy today. Yeah. Incredible world we live in, folks. In upcoming videos, I'm going to show you more. The distance to the stars, to the bolt of the heavens, the celestial dome, the moon. Incredible stuff. We're going to determine the true distance to satellites. I am loaded with information, folks. We're going to look at gravity, anti-gravity. We're going to look at anomalies, gravitational anomalies. I have so many experiments and not enough time. But I started wondering, Where exactly is the sun? And which model predicts its direction more accurately? Is it the flat Earth or the globe? Where is the sun? I thought. By looking at the time tag on the photos, I went to time and date and put those values in, and I got the location to the sun, somewhere in the Atlantic. So I had to measure the distance. I was very curious. The azimuthal equidistant map is more accurate in angles, as you'll see, so the sun is somewhere around there. Using Google Earth, I approximated the distance to the spot on the ground below the sun, and to my shock, it came out very close to around 5,500 or so. Incredible! Even more incredible is the flat Earth predicts the direction to the sun correctly, whereas the globe does not. Just unbelievable, folks. The world is truly flat.